This week, we will be taking about seasonal trend modeling with regression. There are two different types of seasonal variation. These are constant and increasing. Seasonal variation is considered constant if the magnitude of the seasonal swing does not change based on the level of the time series. So if this were monthly data, the magnitude of the seasonal change does not change based on what year it is. The type of seasonal variation is considered increasing if the magnitude is not constant over the seasonal shift. Since we are using least squares regression as our main modeling tool, non-homogeneous variance should be apparent if it exists in the residual plots. As always, we remedy non-constant variation by using a transformation. Let's go back to the beverage data that we saw in the earlier lectures. Plot the data and decide on the type of seasonal variation. Based on the plot, it would seem that the seasonal variability is constant. In the previous example, we used a visual test to decide about constant seasonal variability. This is subjective at best. Do we have some sort of statistical test for equal variance? We could run an equal variance test. You should recall from a previous course that the equal variance tests are called Bartlett's and Levine's tests. Here are the results for those tests for the beverage data. You can see since the p-values are quite large, we should decide to not reject the hypothesis that the variation is constant. Based on the visual check and the equal variance tests, we assume that we do not need a transformation for the beverage data. Be aware that the equal variance tests do not work as well in small sample sizes. Now let's talk about seasonal trend models. If the seasonal variation is constant, then the model in the slide is considered the seasonal trend model. Notice that it has three components: a trend piece, TR, and seasonal piece, SN, and an error piece, epsilon. The trend piece can be anything that we talked about in the last lecture: linear, quadratic, exponential, etc. Here are some of the details for this model. The error terms meets the typical assumptions of being independent and identically distributed with mean zero and constant variance. The magnitude of the seasonal component is independent of the trend. You can look at this as no matter what kind of trend you are dealing with within a seasonal period, the difference between the highest peak and lowest valley will always be the same. This is another way to define constant seasonal variation. We will use two types of regression techniques to create seasonal trend models. These are dummy variables and trigonometric functions. Let's first talk about dummy variables. Sometimes, instead of being continuous, a predictor variable will be categorical. This means that it has two or more distinct levels. From regression, we know that these types of variables have to be treated differently. We must somehow create a new set of variables to take into account the separate deterministic effect that each level has on the response. Using dummy variables, the seasonal component Sn will be defined based on the equation in the slide, where sub c will be 1 for the present time period and 0 for the remaining time periods. Notice that we only utilize L1 time periods, given that the seasonal period has length L. This is because if we used all of them, it would be redundant. The time period that we leave out is now the reference time period. This makes each coefficient have a slightly different meaning than usual. The coefficient is defined as the difference in the response between the present time period and the reference time period. Here is an example of using dummy variables. We will assume that the present time period is the second period. Notice how a 1 has been assigned for x in time period 2 and a 0 has been assigned for x in the remaining time periods. Assume that the LTH period is the reference time period. The coefficient for time period 2 is now the difference between the response at time period 2 and time period L. The new model is given on the screen. Notice that the dummy variable adjustment has no effect on the trend piece. Let's take a look at the atmospheric concentrations of CO2 in Hawaii from January 1956 to January 1997. Create a dummy variable model for the data through 1996 and use the 1997 data to validate your model. Here is a plot of the data. There seems to be a trend and some seasonal component. This is monthly data, so it would seem that L equals 12. The seasonal variability seems to be constant based on the plot. You could do an equal variance test here to confirm if you wish. Here are the results of the dummy variable model with a linear trend. The VIFs for these terms are small, which indicates no issues with collinearity. Also, notice that the reference time period is the month December, so each coefficient is defined as the change in the response between the month in question and December. The RSQ, ADJ, and RSQ pred are both high, which indicates that the model explains a large percent of the variation in the response and predicts well. At this point, you could try other trend components such as quadratic exponential, etc., and compare them with the linear fit. This model fits so well that doing this is probably not necessary. Before deciding on this model, we need to check adequacy. Based on the DW test statistic, we should be suspicious of autocorrelation. We can do the official test to confirm this. Here are the residual plots. You should be able to see very quickly that this model is not adequate. The pattern in the residuals versus order plot is another indication that we most likely have an independence issue. Here is a plot of the sample ACFs for the studentized residuals. An adequate model should have no large ACF values and should die down quickly, which would indicate stationarity. We can see from this plot that neither one of these things are happening. Based on the patterns on the residual plots and the small value for the DW statistic far from 2, we should conclude that the model is not adequate. So we need to somehow alter the model to account for the autocorrelation. We can do this by fitting a model that includes the lagged 1 response values as a predictor. Here are the results for this model. You can see by including the lag term, the model fit seems to be even better. The only drawback of this is that we have introduced collinearity. This is not surprising since we would expect the differenced responses to be correlated with the time period. If this is a big concern, we could remedy the collinearity. At this point, it doesn't seem like collinearity is having that much of an effect. We still have significant partial F-tests and a significant overall regression test. Usually for severe collinearity, these two do not agree. The DW statistic is 2.449. The p-value for the test is significant going in one of the directions. This is an indication that we still have some issues to deal with. Let's look at residual plots. Even though there seems to be some extreme standardized residuals, the plots look much better than before. Let's look at the sample ACF plot for the residuals. We can see that this plot looks much better. It seems to cut off after a lag of 1. This is an indication that we may need to include another lag term in the model. This would be a lag 2 term. We can conclude here that since we still have a significant DW test and a large residual ACF at lag 1, we should try to fit the model one more time and include a lag 2 term along with the lag 1 term. Here are the results for our new model. We can see again that the addition of the second lag term really increases the VIF for the lagged response terms. Again, you should expect this. This is not really an issue considering that we still have significant t-tests. All of the fit statistics are very good, including RSQ, pred. The overall regression test is significant and the DW tests are both not significant. One thing that I did want you to notice is how little the lag 2 term contributes to the model. Let's see if the addition of this variable has taken care of the problem with the residual sample ACF plot. Here is the residual sample ACF plot for our new model. We can see that we no longer have any large residual ACF values. In conclusion, our new model does not yield a significant DW test and has no large residual sample ACF values. All of the model fit statistics are good as well. The only real issue is collinearity. Let's check out the predictive ability of the model with cross-validation. Here is the table of fits, STD errors of fits, prediction intervals, and the observed values for 1997 by month. You can see that the intervals are quite short. Based on the table, 9 out of 12 observed values fall within the intervals. Let's wrap this example up with some conclusions and recommendations. The model seems to fit well based on RSQ, ADJ, and RSQ, pred. The cross-validation shows that 9 out of 12 intervals cover the actual observation. I would probably conclude that this model is usable and continue to collect data to verify. The other type of function used for seasonal modeling is the trigonometric function. There are 2 equations that we can use for the seasonal component for this model. Each is given in the slide. Can you see the advantage of the first equation? This technique can be used for constant or increasing seasonal variation. The first equation can only be used for constant seasonal variability. The second equation can be used for either one. I would urge you to always remedy increasing variability with a transformation first. This is the only situation where you can model increasing variability without it. Based on parsimony, it would be better to use the first equation as much as possible. Of course, if you can't find a suitable transformation, equation 2 is the one to use. Notice also that the model assumes a linear trend. This is not necessary. It can be adjusted for any of the other trend components as well. Dummy variables versus trigonometric functions, which is better? Of course, it depends on which produces a better fit and predicts better. Most prefer dummy variables because it is easier to assess what is happening during each of the seasonal periods. It is also easier to explain. Let's go back and repeat the CO2 example using trigonometric functions. Here are the results. I created the sine and cosine variables by finding the sine of 2 pi t / L and cosine of 2 pi t / L and using each as a predictor. Based on the RSQ, ADJ, and RSQ, pred, the model seems to fit well. The DW statistic is again small. The residual plots show patterns very similar to what we saw using dummy variables. Again, we are seeing the slow die-down pattern for the residual sample ACF plot. Based on the size of the DW statistic, again not near 2, and the patterns on the plots, we should assume that the model is not adequate and autocorrelation is present. We can again try to remedy this with the use of the lag 1 response as a predictor. Based on the analysis, we again see collinearity. We can safely assume that it is not causing an issue based on the comparison between the overall regression test and the partials. The RSQ, ADJ, and RSQ pred are also still quite high, and the DW statistic is closer to 2, although we should check the p-value for the test. Based on the SAS proc autoreg procedure, the p-value is less than 0.0001. This indicates that we still have autocorrelation present. The sheer number of points on the residual plots make it hard to tell about alternating points or clustering. We are still not seeing the quick die-down or cutoff pattern in the residual sample ACF plot. It is not even apparent how many more lags we would want to fit in order to remedy this. Let's try a lag 2 term. Here is the DW statistic and the residual sample ACF plot for the lag 1 and 2 model. We still are seeing the same slow die-down, if at all, pattern in the plot. We could continue to add lag terms to the model, but there doesn't seem to be any logical path to follow for this. At this point, I would recommend using the dummy variable model. Next time, we will talk about exponential smoothing methods.